Okay, so here we are back in the notebook. We have our model. What we're going to do is say model dot, and what we're going to do is say predict underscore generator, and we're going to pass in our test image generator. And then let's go ahead and just call this PRED for predictions. Go ahead and run that. Keep in mind, this usually takes a lot longer than a typical prediction because the generator has to actually go into your computer, read and open these image files, and then feed them back into your model. So if we take a look at the results here of pred, we get what kind of looks a little strange, but essentially you'll notice there are values between 0 and 1. So it actually doesn't return back these straight class calls. Instead, it returns back the probabilities. So you notice that this last one, for instance, is 0.97. So it's 97% sure it belongs to class 1. So what we actually need to do is set predictions equal to pred greater than 0.5. And what's nice about this is if you take a look at your predictions now, this is essentially just true and false statements. So true and false statements are treated as zeros and ones in the case of NumPy. So what we can do is directly pass this in to our confusion matrix and classification report. So again, keep in mind that pred, even though it looks for some of them to be just class calls like 0 and 1, they're actually probability values. So keep that in mind. Okay, and if we take a look at the length of pred, notice it's for the entire test set. Okay, so what we're going to do here is simply say from sklearn.metrics import a classification report as well as a confusion matrix, run that, and then let's go ahead and print a classification report comparing our correct answers, which if you want to get the actual classes, you can say test image generator, grab the actual classes, and it returns back an array of those classes. So that's our Y test values, pass those in, and compare them to our predictions, which recall was this filtered version of the actual predicted probabilities. So we'll grab our predictions here and put them in. So we print our classification report, and you should be getting something around 90%, maybe a little less, but we can see our overall accuracy is 87, or pretty good precision and recall across the board. F1 scores pretty close to 90%. Keep in mind the defaults are going to be 50% accuracy, and the fact that this is saving a lot of time really helps. And what's nice about this model is the fact that it's returning predicted probability is, let's say you wanted to implement this model in real life and actually have it aid doctors. So far we're saying that if we're more than 50% sure that our prediction is infected, go ahead and label it as true. It is infected. Actually, we have to look back here and check so uninfected is actually 1. So the values go from 0 to 1, and uninfected is 1, which means if it's true, that's a 1, we believe it to be uninfected. So what we're saying here is if we're saying with a probability of greater than 50% that it's uninfected, go ahead and just say that it's uninfected. But really what this is going to do is serve as a model that assists a doctor. So we can actually set the threshold higher if we want to. And this is where you can essentially make your own sort of precision recall trade-off. So you can maybe say, okay, I only want to maybe alert the doctor if we're 80% sure or something like that, and have the doctor manually look at everything else. So this is something you can definitely play around with, and it's an important aspect to consider in real life, especially when we talk about things like what's more important, a type 1 error or a type 2 error, or a false negative or a false positive. And we discussed all that in the machine learning overview section of the course. So keep that in mind. This line right here, even though it kind of looks innocuous and just a very brief moment, this is actually probably one of the most important lines in this entire project because it directly determines your precision recall trade-off rate. Okay, so we have our classification report, and we can also perform a confusion matrix if we want to. We can say confusion matrix, pass in essentially this tuple right here. Go ahead and just copy and paste that, and we can see how many we're misclassifying. Okay, so once we actually take a look at that, let's go ahead and show you how to predict on a single image. If we take a look at Paracel, this is a single image, and I can actually show you that image by uploading from Keras preprocessing. We can say from TensorFlow.keras.preprocessing, import an image function. And what's kind of nice about this is there's this load image functionality that's actually built into TensorFlow. Previously, we were using matplotlib, but we can actually do this with this paracel. So we can say image, load image, and it actually displays an image. And if we check the type of what this returns, it's returning back this special kind of pillow image file. So keep that in mind, it's actually not an array. It's this kind of specialized image file. What we're going to do here is, what's nice about load image is not only can we provide the path, but I can also say, what's my target size? And in this case, I can reshape by saying my target size is equal to that initial image shape I defined of 130 by 130 by 3. So we'll go ahead and say, this is my image. And if we take a look at my image, the notebook actually displays it. So we think about this real-world situation, what's actually happening. The doctor is going to essentially email us this PNG file. We'll go ahead and either train our model or load up the model that already exists. And so now we got this email of this PNG file. We'll load it with this command, image.loadImage. We'll check what our target size was, the image shape, and we can always say, if we want to, model.summary, run that, and we can kind of examine the model that we're already working with here. And then what we're going to do is we're going to read in this image and pass it to the model. So how do we actually do this? Well, if we say image dot, there's an img to array, which actually transforms this specialized image object to an array. So I'll say my image array, and now I have my original image, which quite clearly it looks like it's infected given the design. And now let's actually grab my image array, and there we have it. What we're going to go ahead and do is we're going to check the shape, and notice it's 130 by 130 by 3. So what I'm going to do here is simply resize this along the 0 dimension. And I can do that several ways. I can do a reshape, or what I can do is I can say np, and it has this expand dimensions functionality that basically says take in that current image array and expand it so that it has a new image along axis is equal to 0, that very first item. Because really what I want this shape to look like is one image by 130 by 130 by 3 color channels. Because the model expects batches of images. Even if it's just one image, it needs to know that it's a batch of one image. So let's go ahead and redefine that. We'll say my image array is equal to this guy. Now we check my image array, check the shape of it. It's 1 by 130 by 130 by 3. Now it's ready for our model to predict. We're predicting off a single image array, not off a generator. So now I can just say my image array, run model predict, and it predicts it to be 0, which, recall, if we were to take a look at the class indices again, we can do this off train image generator or test image generator, call class indices. It believes this is a parasite cell, and clearly it is. In fact, it was the first image we saw previously. Okay, that's it for this project. I hope you had a lot of fun, and I hope now you explore your own image data sets and start training it for your own classification problems. Thanks, and I'll see you at the next section of the course.